So you can find these slides on the website. I'm not going to use them very much, but just as an introduction. Chapter 6. All right, so Chapter 5 deals with discrete data, like those 3 methods that we learned were essentially how to handle discrete data sets. Now we move on to the most popular, I would say, or most commonly encountered data set in all of science and all of the natural world, which is the normal distribution, which is a continuous data set, because again, it's of most interest to engineers, as it's what's, these are collected from taking readings or measurements, right? Continuous data sets are only as precise and accurate as your instrument allows. Right? Like in lab number 3 that we just discussed. These are, how did they get that data? Well, it's probably they're taking the average and then just looking at a trend, but at least they took an average to begin with, right? They look at historical averages like we just saw there, right? Even temperature forecasting used thermometer was used at some point. If it's the past, then they just averaged everything out, and then they look if it's going up or down. I'm pretty sure that's all they do. Thermometer was used at some point to generate the data, and the thermometer is going to be accurate, or it's going to be not, or it's going to be precise, or it's going to be not. And so your data set's going to be all over the place. Like even if you and I just took a whole bunch of measurements, let's say we all had a thermometer. This is what's going to happen when we do our pendulum experiment after the midterm, when we try and measure the mass of the Earth. There's going to be some people that are going to have a measurement that's too big, and there's going to be some people that have a measurement too small. But when we average them all out, it should equal the actual mass, right? Some people are going to make a mistake on the high side, some people on the low side, and this is why we would call this a continuous data set, right? This could be, and then let's call this, for the sake of today's class, the error on measuring the mass of the Earth. And the average should be 0. If we take enough measurements, the average error will be 0. And this is what's called a standard normal distribution, when the mean is 0. And furthermore, the standard deviation of these distributions is going to be 1. That's what we're going to call, and that's the topic of today, 6.2, the standard normal distribution. Is specifically a scenario where you have a probability distribution where the average is 0. A classic example of this that they use, especially in this textbook, is something called the bone density test. And maybe your mom or your dad, if you have osteoarthritis, bone density. But they also use this in science and engineering applications, like, again, what is the deviation from the average? Or in other words, the error. So you can use this with error analysis. it should be 0, right? The average mistake should be 0. And then sometimes it's too high, sometimes it's too low. And same thing with bone density, right? Sometimes with bone density, it's too high. In other words, 0 is average. And then sometimes you can have weak bones or you can have strong bones, and so on and so forth. So we've seen this before, right? This nice symmetrical distribution that we call the normal distribution. And look what we find here. Our friend Euler or Euler, however you want to pronounce it. I pronounce it Euler, but I've been told it's Euler. I like saying Euler because of Bueller's Day Off. But Euler's number apparently is pronounced Euler, but also as a Calgary Flames fan, I can't get on board. Euler's number, we saw this with our Poisson distribution, and I mentioned to you that it pops up every now and then, and voila, here it is already, making another appearance. God's constant right there. And if you have a situation, if you look how complicated this is, you don't have to worry about this because we give you this curve and everything. You don't have to know this, but if you have a situation where this is 0 and you have a situation where this is 1, this kind of collapses into a much easier, like a much nicer equation, as you can imagine here, right? It's going to be approximately in a standard. So again, this is called standard normal. A standard normal curve is when you have these conditions. And therefore, the equation kind of simplifies itself to more like this, right? It's going to be e to the negative 1/2 x squared over square root 2 pi, which is a lot nicer. But it's, again, a beautiful equation. And you can put it into a graphing calculator, right, and just kind of take a look at it. It's quite beautiful. You can actually approximate it. I used to just approximate it as negative. You can just go negative x squared. That's pretty good. It gives you a pretty good sense of what's happening here, where the average is 0. And then, but again, this kind of gives you a more realistic curve, as if you say, well, let's copy that. So this divided by 2. So you see how that transformation, you guys probably studied that in Math 238, how to transform functions. Maybe not. Maybe it's been a while since you did that kind of stuff. So this is a beautiful formula because it also has pi, right? There's not a lot of formulas that also have pi in it. And E and pi. Wow, it's like a real party. Okay, where's my pi symbol here?
It is near under root.
Oh, very good, thank you. So that's more realistically what it looks like, but beautiful. And these would be standard deviations on the side here. So the area under it, after 2 standard deviations, and so on. All right, but right, because x is your value. So let me just explain a little bit what's going on here. So why are we even bothering with a standard normal? Well, the idea is that every other thing that we deal with, like when we get to the applications, right? It's so rare that your average is 0. Like mostly it's not that, right? Most of your average is, I don't know, like 25 degrees Celsius or whatever your measurement is. And so we're going to have to use an equation And this is the equation we have to use. We learned this in chapter 3, but we have to calculate a z-score when we want to figure out the probabilities of normal distributions. We have to first calculate a z-score, which is whatever value you're interested in, minus the average over the standard deviation. So when we do the applications of normal distributions, or in other words, non-standard normal distributions, where you have to calculate a z-score first, you have to do this. But if you can see how, when you have the conditions here, where this is 0 and this is 1, then your z-score is your score. So whatever number you get on a standard score testing, whenever they give you a number on a standard normal distribution, that is the z-score. Okay. So the types of problems you're going to have to worry about here are things like this. And essentially the main learning outcome for today is how to use your z-score sheet so a z-score sheet or Excel, I'll teach you both. To determine probabilities using z-scores. That's essentially the whole point of 6.2. So remember, the z-score is the number of standard deviations you are away from the mean. And in this case, because the mean is 0 and the standard deviation is 1, whatever your score is, right here, so basically whatever your score is on the bone density test, that's how many standard deviations you are away from the mean. All right, so how do we use the z-score sheets to determine probabilities? Okay, well, you guys already know the empirical rule, right? We learned in chapter 3. In chapter 3, we learned the empirical rule, which basically says that plus or minus 1 standard deviation, 68 or 67% approximately, plus or minus 2 standard deviations, 95, and plus or minus 3. But this is just kind of a range rule of thumb. It's not exact. It's not very precise either. It's just kind of a ballpark. So we want to be very precise, right? Like, let's say if I know that, plus or minus is 67, but what if the question says, what is the probability of getting a bone density test score less than negative 1.5 let's go 1 point. You can even be really precise, as I'll show you. Let's say less than negative 1.52 or greater than, let's say, 0.57. So now we can use some sort of magical chart that I'm going to show you right now. It's on your formula sheet, and if you've been going through, maybe scrolling through this on your spare time, you'll notice that there's all these charts at the end. So we're going to be worried about these guys now, which is table number 1. Table 1, this is of the negative scores. I think they should have called this table 2 because it's on a separate sheet, but they just said table 1 continued. I would have named it like table 1A or something, or 1B. I don't know why they don't do that. I would have done this to make it more clear, but whatever. I'm a bit of a perfectionist, as you've noticed. Although I make I make a lot of mistakes for one, but that's what keeps me motivated. Okay, so table 1A. What does this give us? This gives us the negative Z scores. So what they want us to figure out, what is the probability of, so I'm going to have two really kind of, so negative 1.52 and 0.57. So the first thing you should always do here is draw the graph, okay? If you don't do this, you're going to get it wrong at some point. And the reason why is because people get confused about what area they're actually asking for. So always draw this, especially if you want to get a half mark on your midterm or whatever, because you might get it wrong. So I would always suggest you make a little drawing. And then what you do is you kind of label where these things are, right? So the first important thing is less than negative 1.52. So that would be somewhere below, right? That's going to be somewhere like here. Let's say. Let's call that negative 1.52. Because this is going to be 0, right? And then greater than 0.57, well, that's going to be probably around here, let's say. 0.57. And again, the reason I want you to make these diagrams is so you can highlight what exactly you're looking for, right? I'm looking for less than 1.52. So I need the probability of landing here. And on the other side, I need the probability of landing here, right? These are the key words, less than or greater than, right? And then or as well. So as long as I don't get it in the middle, that's the probability I'm looking for. And the way you're going to have to do that is you're going to have to do a couple of different calculations. So you'll notice that according to the Z-score chart, all of what we're going to be able to, so this is these are the probabilities here, all of these values here inside the chart. These are probabilities, and it's the same thing as the area under the curve. So the area under the standard normal distribution is the probability. That's the genius, again, of Euler's number. Of that value, of less than that value, that's the better word, of less than a given value. And in this case, the Z score. So if I want to know the probability that Z is less than negative 1.52, I have to find negative 1.52 in the Z score column here. So that the first two digits are here. So negative 1.5 would be here. And then I have to, it's kind of a fun game. Then you have to go to this one where you get the third value. Or the second decimal locator. And you would just find the 2. Boom. So that's fun if you're, you know, if you're into this kind of thing. So negative 1.5, this is 0, 1, 2. So in other words, the probability is like 6.4%. 0.0642. So that's this probability here. And then let's say I want to figure out now this one here. So I'll do the same thing. So I go, all right, so the first trick is you find the first 2 digits, right? So in that case, it was negative 1.5, right? And then so that's the first 2 digits. And then the third digit would be 2. And that's in this column here. That 2 is right there. So then you just find wherever the intersection is. They intersect here. So you'd say it's a 0.0643 chance. Whereas so the next Z score I have to look up, right, is probability. So remember this, the problem with this chart is that you're always getting the value, the percentage to the left. So the percentage to the left is the problem here. Like I'm going to want this part here of this guy here, but the probability that I'm going to get is here. They're always going to give me the area to the left of the curve. So this one is 0.57. So I have to find 0.57. So it'd be 0. There's 3 digits. First 2 digits are here. 0.5. Find that. And then the last digit is the 7. So I find the 7 here. So 0.57 would be here. Right? Again, you're just finding the intersection point of one row and one column. So then you would have, right, so that probability of 0.7157, again, is this area here. But what I want is this area, right? I want this area, so I have to subtract it from 1. So the probability that x is going to be greater than 0.57 is 1 minus 0.7157. 0.2843. Something like that. 0.2843. That would give me here. And then, therefore, to finish this off, you would just have to add both of these areas together, right? Because I'm wanting less than this or greater than that. Now, there's also lots, I mean, you can do anything really, but they might ask you, what is the probability that it's, let's say, between 1.21 and 1.62 or 68 or something, let's say. So in this case, your graph, and this is again why it's important to do the graph so that it's not too confusing, or it's not more confusing than it needs to be, is, in this case, you have 0, And then here you would have 1.68 here. And then 1.21 would be over here. So you just got, again, making the drawing really helps. So in order to figure out these, right, that's what I want there. The only way to do this is you have to take the probability of 1.68 or less and subtract it. So you have to take that because it's going to give you everything, right? When I figure out, so let's figure out what the probability, what is the probability that Z is greater than, less than 1.68? Again, when you look on your chart, it's confusing because it gives you everything less than. Like you can't just cut out a smaller piece. So you have to go 1.68. So 1.68. So this is 9. This is 8. One 1.6. This is 9. This is 8. So 0.9535. Right, again, this is the third value. So 0.9535 and then so that's all of this. So that's where you have to be careful, because now I'm going to want to cut out this part here, right? I got to figure out what 1 point, and then when I cut that part out, you're going to get the only remaining part here. 1.2 and then 0, 1. So 0.8869. And that's over here. And then you would have, if when you subtract, now you would subtract these two. So when you subtract these two, then you would get your answer of just the blue area. So it takes just a little bit of practice, but then it'll make sense. And just quickly here, the last type of problem is when you have to deal with the reverse. So let's say somebody said, what score separates the 75th percentile? Right? So let's say somebody said, what score separates the top 25% from the lower 75%? You would have to do the reverse, right? That's the same thing as the 75th percentile. You'd have to say, all right, so I know that I need something that tells me this. In other words, I'm going to look up the area and then find the z-score. This is the same thing as asking for the 75th percentile. Or you could say the top 2%, right? You could do anything like that as well. What is the top 2%? And then you'd have to find the 0.98. So what you do is you go back to your formula booklet and you just kind of do a little bit of detective work and you find 0.75 somewhere in here. And you'll notice that it's rare that you find an exact value. This is usually like the game of Goldilocks, where you have to figure out this one's too low, right? 0.7486 is too small. 0.7517 is too big. So this is the Goldilocks zone right here. And so the way they do it in the textbook, and the way that you guys can do it as well, is, especially when you're putting your answers into Pearson, right? They kind of usually like things a certain way. And so you can say, well, if it's 0.67 is too low and 0.68 is too high, the textbook says take the middle. You could do an interpolation, but they just want you to do this. Just go halfway if it's in the middle. Like something like this would be different. Like if you had 0.86, for example, we'll do more practice like this throughout the whole semester, but you'll see like this one, 0.85, let's say you were looking for 86%. 0.8599 is so much closer than this one. What you do is you're going to start rounding down. So like it's 0.8621. If you round to 3 digits, you get 0.862. If you round to 3 digits here, you get 0.860. So you would take this one, because this is so much, you just keep rounding down until they're the same, basically. But these ones are equally as far, right? If I go to 3 digits, none of them, they're still wrong, right? 0.752, and this one is 0.749, so they're still off. So at that point, you take the middle. We'll talk more about that later, but this is just the Pearson method. You could always do an interpolation, what's called interpolation, but they don't do it in the textbook, so you know, you don't need to do it. This is just it's more of an estimation, and that's basically what statistics is, one big estimation.